bones tell stories that words never can. On this note, a very warm good morning and a hearty welcome to all to the second expert lecture of the International Lecture Series titled Forensic Analysis of Thermally Altered Bone Samples. The function of prayer is not to influence God, but rather to change the nature of one who prays. With these thoughts, we will begin this International Expert Lecture with a moment of silent prayer. A hearty welcome to our esteemed guest, Dr. Tristan, for taking time out to share his expertise. Welcome, sir. I also welcome Mr. Don Cairo, Coordinator of Department of Forensic Science, and the faculty members to this session. A cordial welcome to the students of 5th semester BSc and 1st semester MSc Forensic Science to this session. It is a privilege for me to introduce to the audience an active, young, and resourceful personality. We are delighted to welcome Dr. Tristan K, Assistant Professor and Forensic Anthropology at Maastricht University, for the second talk of the International Lecture Series. Sir studied forensic science at University of Amsterdam after graduating from Leiden University with a degree of physical anthropology. In 2022, Sir obtained his PhD on improving the analysis of burnt human remain at Maastricht University in collaboration with the University Medical Center at the University of Amsterdam. Sir has immense professional experience. He has worked as an independent forensic advisor, autopsy photographer, anatomical technician, and forensic anthropologist. Sir has formed a multi-institutional collaboration partnership with Maastricht University, the University of Amsterdam, and the University of Applied Sciences, Van Hall Leicester, which works on taphonomic changes due to fire, subaerial subsurface, and subaquatic decomposition, focusing on the gap between fundamental research and applied research. Sir has also authored research papers in reputed peer-reviewed journals. We consider it an honor to have Sir in our midst to address the second talk in the International Lecture Series of this academic year, given Sir's illustrious career. Without further ado, I request Sir to address the gathering.
Thank you so much for this elaborate introduction. Now I need to move on to the presentation. All right. So hello everybody. I'm speaking to you as a Dutch citizen from the Netherlands. And this is actually where I live, at the Zaandam. If you ever are able to come over to the Netherlands, please do visit the windmills. However, just like the windmill of my grandfather, it doesn't always go as planned. Sometimes these things catch on fire. And then we need to do an investigation, of course. So that's the topic that we're going to talk about. And unfortunately, some fires, an individual dies. And then we've got a medical legal investigation. The first fire that I would like to introduce is a fire that I've actually seen from my apartment in Leeuwarden when I was there. And this was a pretty big fire. And as you can see, fire draws the attention of a lot of people. Please stay away from the fire. It's not good for your health, although you are curious to see what's going on. What seems to be a pretty simple fire when you're standing in front of it is actually a pretty big fire if you look at it from the sky. So in this case, there are 15 buildings damaged. There was one deceased. And just for your information, this is not only 15 buildings that were damaged, but this was more than 50 residents that are damaged. These are student housings. So the potential of deceased was way higher than the actual amount of deceased, which is, of course, luckily speaking. But we don't know this if we stand at the front of such an incident. We don't know who was in there, how many people were in there. So we have challenges. An investigation is started, and our main objective is the retrieval of human remains. We need to identify human remains if we find them. We apply disaster management, and we consider fire to be an open disaster. And in an open disaster, that means that we don't have any clue on who is involved. That is opposed to a closed disaster. And for a closed disaster, we actually do know who are involved. And a good example of a closed disaster is, for example, an airplane that crashes in an area where nobody was. And we've got a passenger list for the identification. So actually, a fire of a house or an apartment building is a very big challenge. As we all have seen, a lot of people are interested and come to the site. So there is also a very high ethical and social duty for us to carry out the work as good as we can. There is a forensic investigation, so we collaborate with the forensics. And the forensic investigation of the police is mainly focused on finding the source of the fire. So that is in collaboration with the medical legal investigation towards the number of individuals, the number of victims. And we assess the minimal number of individuals, but also the most likely number of individuals. That is based on the body parts that we find. And we're going to look into what can we expect to find. Besides the identification process, we also aim to reconstruct the peri-mortem event. And the peri-mortem event, that's a pretty complex reconstruction. We aim to see what was the amount of damage from the fire to the body, and how does that relate to the forensic investigation with regard to the source and the path that the fire took. And lastly, there is always an investigation by the insurance company, which is similar to the forensic investigation, but normally without a medical legal investigation in the Netherlands. Another example of a fire, the Grenfell Tower in London. And I would like to, well, digitally take you into the tower. So on the right below, we can see the situation within the tower. And mind you, if we're standing outside, we do need to judge whether we can go in or not. And a tower like this has a very poor structural condition after the fire. So getting anyone in there is a very high risk of the people that we're working with. So currently we're investigating ways of doing the analysis in the tower and trying to locate if there are any human remains without putting anyone in. And we have found out that drones are actually pretty helpful. Drones are helpful to get a very good view on the inside without anybody getting in harmful way. But also, drones are able to collect some material. And with that, we can either confirm or exclude whether there are human remains on a specific location. So that's what we think the future will be. However, the drone and using a drone does have its challenges. As we can see, there is a lot of debris. And with the drone, we cannot see what's below the debris, of course. So we're not there yet. Now let's take a look what happens to a human body when it's in the fire. What can we expect? And the variation is rather large. And the variation depends, of course, on the size of the fire, but also on the duration of the exposure and the position of the body in relation to the fire. Most of the times, we as well in the Netherlands are encountered with charred remains. And with charred remains provide lots of information because a lot of the soft tissue is still preserved. Now we can also encounter a partial or even an incomplete cremation. In most cases, we have a partial cremation, and that means that certain body parts, most likely closest to the fire, have been consumed by the fire, and thus we retrieve skeletal remains for those body parts, while other body parts are still pretty good intact. An incomplete cremation, that means that we have almost complete skeletonization, but the skeletal parts are all still in pretty good shape, in pretty good condition, and are retrievable. While a complete cremation, that means we only have the ashes. We see this rarely in forensic casework, but this happens on a daily basis in society during a modern cremation. And for a complete cremation, we actually need a mechanical force to damage the cremated bones. We can expect this actually in an apartment fire when the apartment collapses somewhere at the end of the fire. So during this process, human remains have already reached this partial to incomplete status. And then the mechanical force from a building collapsing leads to complete cremation. Complete cremation is very difficult. If there is complete cremation in a forensic setting, it actually means that you are most likely not able to recover the remains. Now on the right, I've also indicated the chance on the criminal activity. Charred remains are so often encountered after fires. That doesn't really tell you that there is a chance on a criminal activity. However, especially if the remains are somewhat in a further state of damage due to the fire than the surrounding, than the room that the body was found in, that's the moment that we need to think, all right, it doesn't match. The reconstruction doesn't match. So maybe a perpetrator has tried to cover up evidence or tried to get rid of a body and has placed some extra material like a fire accelerant or something that has good burning qualities at or around the body. Unfortunately, the chance on identification diminishes with an increase in damage to the human body after the fire. Charred remains are always pretty good identifiable, especially with DNA. However, when we're getting into the incomplete cremated material, it becomes very challenging, and we need to be very informed on what can we use for DNA analysis and what will most likely not yield any DNA anymore, because we also need to think about resources. A DNA analysis is still not one of the cheapest ways for identification. We also need to think about the ethical part of it. If we're going to grind up every bone for DNA analysis, we're unable to present any remains anymore to the relatives. So therefore, you need to be very informed on what will yield the highest chances for the DNA analysis. And we're going to look into that a little bit. So with regard to human remains, this is what we can expect. And not all of this is human. And that poses another challenge when we're dealing with this kind of material. If there's been a house fire, there's also a chance that any domestic animals inside the house, of course, have died. and are amongst the material that we need to investigate. So just like other standard physical and forensic anthropological analysis, we start with the questions. Is it bone? Now I can assure you everything that's on this slide is bone, although you might not expect it at first. Second, if it's really bone, is it also human bone? Because if it's not human bone, we don't need to do the entire analysis on it. Now, the bone on the lower right, that's not a human bone, but it was found in a house fire incident. I would also want to stress discoloration that we're looking at. One of the major difficulties of this investigation is that the material that we're looking for has the same discoloration as the rest of the site. Thus, by the human eye, it can be very difficult to differentiate between the debris of the house and the human remains. All right, so how long does it take for a human body to get into that complete state of cremation or before the skeletal remains are being exposed? Literature is there on this topic, and from that literature, it's clear that it takes between somewhere 15 to 20 minutes to what then we call deflesh the human remains and the first exposure of the bones to the fire. And that actually also means that not all parts of the body are exposed to the fire at the same moment. Of course, the outside skin layer is, but some skeletal elements will be exposed to the fire earlier than others. And we need to take that into account when we're analyzing skeletal remains after the fire. Like I said, we need to find remains like these in the situation below. And I wish everybody that's taking up that challenging task good luck. So we thought about that. Can we find methods to improve the retrieval of the human remains on the site? And that's when the idea of luminescence came about. So human bone, well, actually all mammalian bone, has luminescent properties. And that means that there are proteins, and not only proteins, but there are a lot of proteins in the bone that when they're excited with light in a specific bandwidth, these proteins have electrons and they move from one electron shield to another. And when they fall back down again on the molecular level, that's the moment they release photons. So while you're exciting with light, the bone starts to release photons. And you can see that, you can see the light that comes from the bone if you use a long pass filter. And with the long pass filter, you actually block the light from the light source. So let's just say I have a strong light absorbing surface and I put on my light source and I use my filter. It's going to be a very dark room. But if there's anything that luminesces, that produces light, I'm going to see those things laying on the floor or among the debris producing light. So we thought, all right, if human bone has this property, producing light, can we maybe use it in that difficult setting among all the structural debris to find the human remains? So we did the test. We heated up human bone sections and checked the luminescence. And on the left, you can see the situation on the white light. So there is discoloration due to the heat. That's what we expect. And on the right, we can see the same samples during luminescence imaging. So now we have a camera instead of my own eyes with goggles on, but the camera has a filter on, and I'm taking images while exciting the bone with a light source in a dark room. The interesting thing from this experiment was, of course, the fresh bone, as expected, produces a lot of light, and the fresh bone is the one in the upper left corner of each image. But what we call the calcined remains, and calcined means we only have the bone salts left on the lower right corner. So that's the very high temperature that's going around 800 degrees, what you can expect in a, well, a good fire. Actually also still produces light. Bone, that's only bone salt. So the proteins that I was talking about have been burned away. Those have been consumed by the fire. So I only have salts, and those salts actually produce light. There is only one difficulty with this technique, and those are the charred bones. And the charred bones contain a lot of carbon, and the carbon is blocking both the light that I shine on the bone, but also the light that the bone is producing. So the blackness of that carbon is absorbing all the light. So that's the only temperature range that's not working. That's around 400 degrees Celsius. But overall, if we look at the entire range, we thought, well, this may work. This may work in a difficult setting. Here we can see human remains retrieved after cremation. And I've cited it. So what we have is we have the diaphyseal sections on the lower right. We've got a row of ribs on the middle left below, and then we've got some cranial fragments upper left, and the epiphyseals on the right. And just let's look how this looks if we use the light sources. So this is what it looks like. And this is actually a pretty interesting result, because now we have got some, well, it's subjective, but let's call it green luminescence all over the place, but also some orange to, well, almost brown luminescence going on. And that's not what we expected from the previous slide, because this was our simple experimental setup with an oven, and this is after the fire. So what's going on here? Well, apparently, if temperatures exceed 800 degrees, the periosteal part, which also contains a lot of iron and other ions from the body, actually takes on a different color of luminescence. But you do need to go over the threshold of 800 degrees. So this actually tells us also something about the exposure temperature. So the locations, and there is one very particular in this image that still exhibit green luminescence, have been shielded from the fire for some duration, or not exposed to the intense heat, at least. And in this case, it's the pelvic part. So here we have the acetabulum. That's the part where the femur connects with the pelvic area. And that part has been laying on the ground, face down, and thus was shielded from the fire. And these things become interesting, because if you're going into DNA analysis, we want to select sections, we want to select parts that have been exposed to the lowest temperature, of course. So that helps, but it also helps to say something about position. And in this case, the majority is orange luminescence. So the majority has been exposed to a very high temperature, meaning it was pretty close to a source of the fire. Now, how should we approach a fire setting? You should always approach it with a grid and collect the remains, or collect anything in that grid. So my advice now is, please collect the things in buckets or anything from the grid. So we know A1, B3, and C4. Those are the coordinates. And then we'll bring them to the lab. Because we have found out that it is pretty difficult to send in our investigators with light sources and goggles and completely make the situation dark, because it doesn't really work. And it also creates more risk for the investigator. So currently, our advice is bring it to the lab, bring it to the morgue, and at the morgue, we empty the buckets, which we know the coordinates, and then we go through the debris. And in this setting, we can use the light sources. We can easily turn off the light, and we can just go through the material with light sources. And the yield is actually pretty good. And of course, if I have very well trained forensic anthropologists, they will still find bones pieces among the debris without the light source. But if we have got a bigger situation, and I'm also working with untrained anthropologists, but they are police investigators, then it's a very easy task to tell them, please pick up anything that lights up. And then the anthropologist can go through everything that has lit up. And no, they don't only collect bone pieces. There are also pieces of plastic, etc. So there is still a task after this analysis. You still need to go through everything and remove the plastics or remove anything else that apparently also luminesces, and those are false positives. All right, so when we've collected all the bone pieces, we need to create some order because it's pretty chaotic. And for this, we can either sort it. We can sort it on size, that's what we've done here. We can also sort it on the discoloration. It kind of depends on the question at hand. If we're going into a DNA analysis, most of the time, we will be sorting it on discoloration. And we also use the discoloration to create the heat maps like this, like which areas of the skeleton have been exposed to more or less heat. And that has to comply, of course, with the expectation. Here we can see in more detail what happens with the color of the bone. And we have tested the subjective methods that are out there, just asking people, if I take a random sample that has been discolored, please can you say something about the temperature that it's been heated to? And those subjective methods don't work that well. They're very inaccurate. People make mistakes if they're using inaccurate and subjective methods. Therefore, we compiled and we drafted a model, and with the model we can estimate that the exposure temperature without the subjective nature saying something about the color. So we're going to measure the color with a program. And for that, we select our area of interest. Of course, we start out, that's very important, with a calibrated image. That calibrated image is loaded in ImageJ, which is a free software kit all around the world. You can download it. And then you need to extract color data. And the color data that we extract is actually in the LAB system. And the LAB system is different from the red, green, and blue system. So sometimes if your settings of the camera, or if it doesn't capture in red, green, and blue, or it doesn't capture in the LAB, but in red, green, and blue, you need to convert the image, which is pretty easy. So convert the image to the LA and B system. You can see it on the left corner. It's a sphere. You get lots of color coordinates. And of all those color coordinates, only the L and the B value have to be used for our model. Again, you select an area of interest, and you can expect variation in a single bone. So document for your analysis what section you used, what and analyzed, and please divide the bone into different sections already based on your visual observation. And then measure the color. All right, big image. So I told you we need the L and the B value, and in the upper left corner you can see the scatter plot of the L versus the B. Now we have already included some colors, and those colors reflect the temperature. So there is some kind of circular pattern here. We start out in the middle right, and then we go down to the lower left corner, and then all the way up to the upper left corner. And that's the circle that we're doing, and we use the cluster analysis on that data. So then we go to figure 2, and we were able to create 7 individual clusters. Now, each of those clusters has its own temperature range, which we can see in figure 3. For example, cluster 2 is a very small temperature range of around 275 to maximum 350 degrees Celsius. Now, if I have an unknown bone sample and I measure it on the L and the B value, I can actually use those in gray, those thresholds that are there, to decide in which cluster is this single bone sample, and then get from figure 3 the associated temperature range. This has an accuracy above 90% for a data set of unknown samples, which was way better than the subjective one that we asked all the forensic anthropologists just to say something about the temperature. So this is what we are using. And of course, we're not using this for every single bone. We're using this for bones of which we want to know, do we want to send these bones in for DNA analysis? Currently, if you're in cluster 1 or in cluster 2, then it kind of makes still sense to send it in for DNA analysis. If you don't have any cluster 1 or 2, but you do have some cluster 3, please try cluster 3, but we know if you're cluster 4 and above, there's no way you're going to get any DNA out of it anymore. Now we also do that reconstruction, and I also already told you about that orange luminescence. And that orange luminescence starts at 800 degrees Celsius, but it increases also with the duration of exposure. So this is something that we still need to figure out how to model, or if we can use this information, because we've got, of course, two variables like temperature and duration of exposure. Now let's take a look at what happens inside of that bone if we're going to heat it up. What happens to heated cortical bone? And I say cortical bone because if we are in a fire scene situation, the chances are biggest that you find cortical bone sections, because the trabecular bone, the epiphyseal ends, they are pretty brittle. They break easily. So therefore my focus has always been on the cortical bone sections. Here we can see the microscopy of it. And in the upper right corner, that's a hemotoxylin eosin stain of human bone. And we can see it has a very neat microstructure of what we call osteons, which are the circular structures in the bone. And there are osteocytes, and those osteocytes are those little white holes in it. And normally in those little white holes, there are the osteocytes that live. Those are the living bone cells. And if we're going to extract DNA from human bone, that's where we want to get that. Those are the cells that we want to get. So it's very important that we understand the damage to the bone structure if we want to say something about the probability of obtaining the DNA out of there. And if you want to get DNA from those osteocytes, you use what they call ancient DNA techniques. That's the same technique that they try to use on dinosaur bone, for example. So that's pretty elaborate. That's not a simple extraction technique. It's a very, very difficult process of getting it out of there. Bone also has another neat feature, and I mainly use this also for deciding whether if it's very fragmented, if I'm dealing with human or non-human bone. This is the birefringent characteristic when we use circular polarizer on the microscope. And what we're looking at, and those are all the white bands in the image. Those white bands, those are strands of collagen, and human bone has a different type of collagen strands in the bone, non-human bone. So therefore we can use it to discriminate. But also remind you, this is non-heated bone. And we had no clue on how this would look if we would use heated bone exposed to the fire. And that of course goes into a gradient. So we start out at 200 degrees Celsius. And here we can see already that the space between those osteons easily is damaged due to this thermal stress than the osteons. So the osteons are actually pretty well preserved at this temperature. And there's still even some birefringent of the collagens, and those collagens break down due to the heat. Now let's move on to 150 all the way up to 400 degrees Celsius. And those 400 degrees Celsius in the upper right corner, those samples have been almost completely carbonized inside out. So it's not only that outer layer, the bone on the outside that is black, it's also black on the inside. But it's very, very unfortunate. Bone, cortical bone, heated to temperatures of around 300 degrees Celsius. Those osteons that we talked about, they act as chimneys, as air ducts in the bone. And where there is air, you get combustion. And when you get combustion, you get. And here we can see the black carbon dots in the bone. That's where our osteocytes were. Oh, and that's not good, because we need those osteocytes for the DNA. So that's very unfortunate. And it's already around the 300 degrees Celsius. So therefore, 300 degrees Celsius is already a very cumbersome temperature for extract DNA from bone. Well, when you're below 300 degrees Celsius to 250, you've got a very good likelihood of still extracting DNA. So this is what the histology told us. The birefringing technique, so the white lines that we can see if we use a polarizer, they diminish, they're gone because the collagens are destroyed again. You can still see them at 250 degrees Celsius. So here we can see some literature on obtaining DNA. And some literature on clusters and the luminescent intensity that I've attached to that. So Fredericks was able to still obtain DNA from bones heated to 200 degrees Celsius. That's about the highest currently is out there. Imaizumi also confirmed the 200 degrees Celsius. We at the Amsterdam AMC, we used that dinosaur technique, and we were able to get the DNA out of bones up to 300 degrees Celsius for a short duration of exposure. And there we go again, duration of exposure, most often overlooked variable. So you hope that the bone has not been exposed to a certain temperature for a long duration, because that really, well, negatively influences your outcome. I'm going to finalize it with some fractures. We've talked about lots of topics, but when we're seeing bones from a fire, these bones have always been fractured. And then when you're doing a forensic investigation, everybody always wants to know, was this fracture already there before the fire? Or is this fracture from the fire? Or did it happen somewhere after the fire? And well, this is one of the most difficult tasks, I think, for the forensic anthropologist. So how does it work? Well, let's just say I take a bone, and on the right side we've got a completely carbonized bone, and we can see from here already, and let's just see if I can get the pointer on. I think I can, and there's my laser pointer. This part, this is a fracture surface, and this fracture surface is completely carbonized. It's just as carbonized as that outer layer of the bone, the perosteal surface. That actually means that this surface has gone through the same change, heat change, as the rest of the surface. So most likely it has been there since the start. But we also need to zoom in a little bit more. Here I have a fracture, which was like a transverse fracture. And this fracture has a very calcined outline, while being still on the fracture surface carbonized on the inside, making it more likely that this fracture occurred after the fire, because this should have been calcined if it had been heated to the same as the periosteal surface. So this is one of the more easy way of distinguishing. And most of the times, if you find linear of those transverse fractures with that big temperature estimation difference between the surface of the fracture and the periosteal surface, if you find that the time you're looking at a handling fracture, somebody picked up this bone and this bone is very brittle and it breaks when you pick it up, resulting in things like this. So is this all there is to it? Well, no, that's not all there is to it. On the right upper corner, we can see bone that has on the fracture surface almost color as the periosteal, resulting in the hypothesis that this fracture has gone through the same heat-induced changes. And here in the right corner, we can see a gradient. Believe me, this bone is completely calcined on the outside, but there's a gradient going on. And that's the moment that I'm a little bit hesitant on my conclusion. I'm not going to conclude it as hard as I can conclude this one. And that gradient also has to do with the adipose tissue that's in the medullary cavity, that cavity within the bone. There's lots of grease here, and that grease is a very good source for a fire. So, and when a bone breaks, this is going to burn. So you've got a very local burn pattern. This makes it a little bit difficult. When bones are completely calcined, it also becomes a little bit more difficult to conclude these things because you need the carbon to really be able to conclude things about this question. As we can see here, we've got carbon on the inside and we've got calcination on the outside. And that means that don't judge a bone on its outside. Always judge a bone on its inside, just like how we should treat each other. All right, so the bone on the inside is normally walking behind the outside. So I always break them. I mean, it's not a nice process of breaking bones, but what I'm looking for is those hidden patches of carbonization, of fresher bone. And with the fresh bone, that's where I'm going to extract for DNA analysis. So I'm never only looking on that outside surface. I'm always going in the bone, opening up the bone and checking how is this bone, how is its microstructure and its situation on the inside. And that is what I want to conclude. Thank you for listening to me. I'm very, very curious to your thoughts and questions and ideas.
Thank you, sir, for this engaging and profound session. The session is now open for the questions. If any student has any questions, kindly unmute yourself and ask the questions one by one.
Excuse me, ma'am. Can I ask a question?
Sure.
Yes, sir.
Can I proceed?
Yes, please ask.
Okay. I loved your talk, sir. It was very interesting and very amusing. But one question I have, can you elaborate more on like the difference in the fluorescence while the temperature is changes? Like how can we use it to position the body?
Yes, let me get back to that. Almost there. Right. So I think this image best reflects, and I'm going to use my pointer. All right. So as I have told you, the red or orange luminescence that we can see over here, it only happens when bone is being exposed to temperatures above 800 degrees Celsius. And that has to do with changes in the molecular structure. So I know these bones, most of these bones have been exposed to a very high temperature during the fire. And then I also expect it to be either at the origin of the fire or at least in its path, right? Not somewhere on the side. But this bone over here exhibits green luminescence at the outer rim of the acetabulum. And that outer rim has been laying most likely on a surface downwards. And if it's in contact with, for example, the floor or something is on top of it, shielding it from the fire, it's still being exposed to a high temperature because this entire room is going to be about 600 to 700 degrees Celsius. But the direct contact with the fire leads to that 800 degrees Celsius. So this part of this skeleton is lacking behind in exposure as opposed to the rest. So my eye immediately go to this bone sample, and I'm going to break this bone sample open, and then I still hope to find carbonized bone on the inside. Does that make some sense?
Yes, sir. Yes, thank you.
All right.
Any more questions?
Ma'am, there's a question in the chat box.
Let me see if I can get it. So I'm in the screen sharing mode.
Okay, Dr. Tristan, I'll read out that question. So one of the students has asked, are there any virtual non-invasive methods to analyze remains at a high-risk scene?
So non-invasive methods. Being invasive to the human body, I then suppose. Because being invasive also means being invasive to the fire scene. And if you go into the fire scene, you also change the fire scene, which is of course for a forensic analysis also cumbersome. But we now look at the human body. A non-invasive technique that might provide information on the microstructure would be micro-CT. And micro-CT can tell you something about microfractures in the bone, and the microfractures in the bone are either from mechanical stress, so a defense wound fracture, for example, or microfracture also occurs due to the heat. But if you use the micro-CT, you're not getting a lot of information on the relations between where the carbon is or where the carbon is not at this very moment. So we've got no data on the grayscale of the CT data that it produces a grayscale. And I would expect from those images in the difference in the signal that you're getting, that you can say something about the degree of the carbon in there. But the literature, the research on this topic is super, super scarce. So I'm still awaiting the radiology departments to go into this and trying to get them that far. Because, for example, in the Netherlands, everybody from a fire scene goes through a CT. But that's just a plain CT, not a micro CT. And I do think that we do need micro CT to look into the bone, to look into the changes of the structure. So that would be the only non-invasive technique for the future that I think is going to help us out.
Thank you, Dr. Tristan, for that answer.
Sir, there is another question. Can you determine if any accelerant or chemical were used in the burning process? If so, what type of accelerants were used?
Yeah, this is often asked if there are any accelerants used. And of course, if the perpetrator, if there's a perpetrator in a case, uses a violent accelerant like gasoline or like benzene or whatever, there is a liquid spill. And we really need the fire scene analysts to find that. And it can be pretty difficult if the fire in a certain area has gone on too long, because then you've lost all your trace information. what we have had, and not with the remains all the way up to the partial cremation or the material that we're now looking at on the screen. That's too far away from being useful. But if you have a body laying on the floor and somebody spilled some gasoline over that, there is going to be gasoline between the body and the floor. That's your best situation, because the human body is going to shield the fire and the gasoline from each other. So below the body, best chances of finding something. But I have also worked in cases where the perpetrator used paper towels and made balls out of that and placed it all throughout the building. Now, no way that we're going to find traces back from paper towel as a fire accelerant. So there are so many options, and you, I think, as an investigator, need to be so lucky to find some traces back if the fire has continued for a longer duration. Of course, in the Netherlands, the fire department can be on the location in 5 minutes, and then a house fire burns maybe for 20 minutes, and that's a very short duration. And then you've got the chance to recover some fire accelerants. Yeah.
Thank you, sir. So there is another question. Are there any other unusual or noteworthy findings during the analysis of the burn wound that require further investigation?
Could you please repeat the first part of the question?
Sir, any other unusual or any other unusual findings during the analysis of the burn wounds that require further analysis?
So the thing is, we are still, especially when we're using things like luminescence, if we're using colorimetry, we're still finding things that we cannot explain. And especially with the luminescence, if an individual was wearing synthetic clothing, which is also as a very strange molecular composition, and those synthetics, they find themselves back on the bone, and then you've got like patches, like strange luminescence. Well, I now know from experiments of combining the synthetics with the bone what that leads to, but it does change the things that you see. And that actually means at this moment, if I see things that I cannot explain, I need to ignore that. That's an artifact. So yes, there are artifacts from the fire that we cannot explain in these analyses. We also have had implants in bodies, which can be very helpful for the identification process. But 10 years ago, more metals were used in implants than today. Today, the medical science uses way more plastics than 10 years ago. And again, those plastics, they do not hold up to the fire very well. So, but they will sinter. That's what we call sinter. If you've got the bone structure on one side and some kind of a plastic on the side, they will go together and be one structure. Yeah, is that bone? Is that not bone? It looks like bone. It doesn't feel like bone. Oh, it doesn't weigh the same as bone. Oh, I don't know if this is bone. So yeah, those things happen in the field. Yeah.
So we have another question from the student. Is the method only for victims in the fire incidents, or it can be applied to radiation victims as well?
Radiation victims. In my understanding, severe radiation victims also exhibit burning lesions. So I have no experience with the degree of radiation exposure leading to changes in the bone structure. I've never investigated anything like that. So at this moment, I need to tell you, I have got no clue.
There is another question. Is there any other method to understand the trauma suffered by a victim of burn other than fractures?
The question is about fractures, I believe. And could you please do the first part of the question again?
Basically, they have asked about the case of partially burned bodies in suicidal cases. Can partially burned bodies be seen in suicidal cases? And are there any other methods to understand the trauma suffered by the victims of burn other than the fracture?
Yeah, so if we have bodies partially burned, carbonized, not yet skeletonized, and you're wondering whether there's trauma, as an anthropologist, I work with the bone, and if I have a body that still has soft tissue around, I work with the pathologist or the forensic medical doctor, and then we discuss whether what we see are actually lesions, if it's trauma. But we also need to realize that post-mortem, a lot of changes occur to the body, to the soft tissue, and it can be difficult to deduce whether something is trauma. Also, I've had one case of a very elderly lady with osteoporosis, and she was caught in a fire. Unfortunately, she died, and her bones, multiple long bones, they broke due to the fire. But it had to do with the shrinking of the muscles, and the shrinking of the muscle was stronger than the bone structure. So I had lots of what could be trauma. It had the same morphology as trauma, but it was no trauma. So we always need to also to take in consideration the pathology of an individual.
Thank you so much, sir, for patiently answering our questions. Gratitude is the fairest blossoms that springs from the soul. On this note, I would like to extend my heartfelt gratitude to our esteemed guest speaker for gracing us with their insightful lecture today. Your presence and words have truly enriched our understanding and broadened our perspectives on forensic examination of thermally altered wounds. Your passion for the subject was very evident in every word you spoke, and it has inspired us to delve deeper into this domain and explore its complexities further. Your willingness to share your expertise with us is truly commendable, sir, and we are grateful for your time and effort that you invested in preparing these lectures and delivering it here. Once again, thank you for enlightening the lecture. We look forward to possibilities of welcoming you back in the future. Your presence has made a significant impact here, sir, and we are truly grateful for this. Thank you so much, sir.
Thank you so much for having me.
The session would not have been possible without the support and the guidance of the members of the management, led by the principal, Reverend Father Dr. Augustine George. Thank you, Father. I extend my gratitude to Dr. Callistus Jude and Professor Don Cairo for encouraging us to strive better and helping us conduct such programs. Thank you so much, sir. The smooth conduction of the guest lecture is because of the faculty members of the Department of Forensic Science. I thank all our dear teachers for coordinating the program to make it success. And a special thanks to Mr. Mayank Raiburi, sir, for ensuring a technically smooth session. I would also like to extend my thanks to all our dear students from BSc and MSc Forensic Science for being a great audience. Thank you to all dear students. Now, as we have come to the end of the program, I request everyone to join together for the college anthem.
Like a golden disk, sun in the rising east, lights up a life divine, fills knowledge in our minds. Laurels and the book make us sublime. With the mighty Lord, we soar high on the bedrock of faith. joy and peace sprawl our hearts and minds. On we march our goals as a beacon for the world, with a passion for our growth and a love for humankind, united and strong in excellence on the bedrock of faith, integrity of force, human dignity true, excellence we strive. Christu Jayanti light and prosperity. Christu Jayanti light and prosperity.
Now I request all the participants to please turn on their videos for a photo screenshot of this session. Thank you, everyone. The feedback form link will be shared with all the participants. And I request everyone to please provide your valuable feedback. Thank you so much, everyone, for today's session. Thank you so much, sir, for today's session once again.
Thank you, sir, so much.
Thank you so much, Dr. Tristan, for being here and covering that exhaustive way. Very interesting lecture. Thank you so much.
I request the host to end the meeting.